Hello there! In this video I will talk about the derivatives of trigonometric functions, more specifically tangent, cotangent, secant, and cosecant, using a geometric point of view. That is, I will find expressions for these derivatives using only circles, triangles, and angles, and so on. This video was highly inspired by the third episode in 3B1B's calculus series, in which Grant already showed the idea of finding the derivative of sine and cosine using geometric constructions. What I'll do here is expand this idea to the other four functions. However, more than just show you a deduction of these formulas, I want to raise a discussion about one of the most fundamental ideas in calculus, to let something approach zero. What conclusions can we take when we make a variable goes to zero? What can't we say? What approximations are we allowed to make? Which of them aren't we allowed to make? By the end of this video, I hope I can give you a good intuition on how to answer to these questions. So let's get started with the tangent one. So initially, we have a certain angle theta, whose tangent is this side of this right triangle. Now we increase theta by d theta units. As a result, its tangent increases in by d tangent of theta units. The derivative of this function will be the ratio between d tangent of theta and d theta, that is, the little nudge to the output divided by the nudge to the input that caused it, as d theta approaches zero. So the key idea here is to make a right triangle, to construct a right triangle whose sides are multiples of d tangent of theta and d theta, and has an angle of theta, pretty much how Grant did in his video. So let's start analyzing things. Here d theta is an angle, right? However, as we are working with a circle with radius 1, we can also see d theta as being the length of the arc determined by d theta. So this little arc over here has a length of d theta units. And here calculus comes into play. This d theta here is not a straight line, it's an arc. However, as the value of d theta gets smaller and smaller, the closer it is to being a straight line. So as we're making d theta approach zero, we can consider this little arc here to be a straight line. It is important to see that we can only say something like this because this is an approximation that never stops getting better. That is, it doesn't matter how small d theta is, there will always exist another even smaller d theta that makes this approximation even better. Furthermore, we can say that d theta doesn't approach a random line. It approaches the line that is tangent to the circle and passes through the point determined by theta. So we can also say that at this point d theta is perpendicular to the radius, right? So for now we are done on the bottom part of our diagram. So let's climb up there to see what we can do with d tangent of theta. So in order to put our main idea in practice, I'll construct this little triangle here, which is zoomed in here. In such a way that this angle over here is 90 degrees. Now the question is, what is the size of this side of our triangle? Well, it looks like, let's call it x. Well, it looks like it has something to do with d theta, right? Because its length depends directly on the value of the d theta. But how exactly? Well, to answer that, we must use the fact that the hypotenuse of this little triangle here is actually the secant of theta. Knowing that, and we can look at two triangles here. The first one here and the second one, the bigger one, over here. Well, they are similar to each other, right? Because they both have a 90-degree angle and they both share d theta. And that lets us write that x divided by d theta is equal to the hypotenuse of our triangle, which is the secant of theta, divided by the radius of a circle, which is 1. So we get this expression. And rearranging things, we get that x is d theta secant of theta units. So great, we now have our triangle that relates both elements we want. Oh, d tangent of theta is here, d theta is there. So the next question is any of these three triangles theta, is any of these three angles equal to theta? Well, we can see that if this angle is theta and this angle is 90 degrees, the last one up here must be 90 minus theta in order to sum up to 180 degrees, right? Because they're all in a triangle. So if this angle is 90 minus theta, this is 90 minus theta. They are the same. And here we have that 90 minus theta plus 90 plus, let's call this angle alpha. We have that this also gives us 180 degrees. So doing the calculations, we actually get that this theta, well, it's actually, this angle alpha here, it's actually equal to theta. So yeah, indeed, our triangle, theta is present in our triangle. So we can already see where we are heading to, but there is only one little detail. Is this a right triangle? Well, initially no, because that would mean that these two lines are parallel to each other if this angle were 90 degrees, which is not true because they both pass through the origin. So what can we do now? Here, calculus helps us once again to get out of this troublesome situation. As we choose smaller and smaller values for d theta, more and more the value of this angle over here approaches 90 degrees. It will never be 90 degrees as we just saw. However, this is an approximation that doesn't stop getting better. That is, it doesn't matter how small our chosen d theta already is, there will always exist another even smaller d theta that makes the value of this angle even closer to 90 degrees. So this fact allows us to consider this to be a right angle. And after all of that, we can finally relate d tangent of theta and d theta. Well, in our triangle, d tangent of theta is the hypotenuse, and d theta is present in the adjacent side relative to theta. Well, adjacent and hypotenuse, the trigonometric relation that relates these two is the cosine of theta. So we can write that the cosine of theta is the adjacent over the hypotenuse, which in our case is d theta secant of theta and d tangent of theta. So as I want this guy on top of this one, I will invert both fractions to get this expression. Now we can remember ourselves that 1 over cosine, well, that's actually the definition of the secant of theta. So we get this, and simply passing the secant to the other side, we get that d tangent of theta divided by d theta, the derivative of our expression, is secant of theta squared. Interpreting problems using a geometric line of reasoning will always let us look at a problem in a new and interesting way, but it also has its defects. In our situation, we have to be very careful about the sign of what we just got, because if it's negative, that won't be pointed out automatically by our deduction. So we need to manually check if the sign is correct. So let's see. The tangent is an ever-increasing function, so at any point its derivative must be positive. And what we just got here, well, we are taking a number and squaring it, so yeah, the result will always be positive. So this must always be positive, this is always positive, so we don't need to worry about the sign in this case. In fact, we can use this exact same line of reasoning to get what the derivative of the cotangent must be. The only difference is the sign of the expression. As cotangent is an ever-decreasing function, that means we will have to put a negative sign in its expression. I'll actually leave here a drawing for you to pause and get to this conclusion by yourself. I also said that we would see the deduction for the derivative of the secant function. And the best part of it is that we don't need to start all the way from the beginning. We can use the same diagram we used before. Look at our triangle once again. Look at the third side of it. We haven't spoken anything about it, but what is its size? Well, it turns out, as we'll see in a moment, it is exactly d secant of theta. So let's reason through why is that. As we said before, the hypotenuse of this triangle over here is the secant of theta, right? So as we increase theta by d theta units, the hypotenuse of the new triangle over here is d secant of theta units larger than the previous hypotenuse. So looking at our diagram, we can already see that it seems like this side of our triangle represents this difference between the two hypotenuses, and hence is d secant of theta. However, we must make a more rigorous analysis of this situation to claim something like this. We have two distinct things. First, we have the real value of d secant of theta, which can be seen like this. We get the first hypotenuse and turn it until it hits the second one. This segment over here represents the difference between them, and hence is d secant of theta. And second, we have the opposite side in our triangle, which was defined like this. Starting from the end of the first hypotenuse, we trace a perpendicular line to it until it hits the second one. This segment on the top here is our side. Visibly, they are not equal to each other. Here I have them both drawn at the same picture, and we can see that, well, this one over here, the bigger one, is d secant of theta, and the smaller one is our side of the triangle. They are not equal to each other, and in fact they'll never be. However, we can see the following. As we choose smaller values for d theta, the lengths of these two segments become more similar to each other. Look here. And this is an approximation that never stops getting better. That is, it doesn't matter how small my chosen d theta already is, there will always exist another even smaller d theta that makes this approximation even better. This fact that is appearing for the third time in this video is what allows us to say that when d theta goes to 0, the opposite side in our triangle approaches the value of d secant of theta. So after that, we can consider this side of our triangle to be d secant of theta. And now it's easy to finish things off. We need to look at the tangent of theta, because that will relate the opposite side, where d secant of theta is, with the adjacent side, where d theta lies. So writing down the equations, we get that the tangent of theta is the opposite over the adjacent, which is d secant of theta divided by d theta secant of theta. So just rewriting things, we get this, and now passing the secant to the other side, we get that the derivative of the secant function is secant times tangent. When I was first learning the derivatives of trig functions, this triangle helped me a lot to memorize the tangent and the secant ones. So just as before, we can actually use the same line of reasoning to discover what the derivative of the cosecant must be, because this side over here will be d cosecant of theta, right? The only difference is, once again, the sign of the expression we get, because if we go on with this process and discover the derivative of the cotangent, we will get that it is, spoiler alert, cosecant of theta times cotangent of theta, which is not quite true. Let's see why. Well, let's see the first quadrant. In the first quadrant, cosecant is positive, the cotangent is also positive, so their product will be a positive number. However, in the first quadrant, the cosecant is a decreasing function, so its derivative must be negative. And here is the problem. This must be negative, this one is positive. So to fix this, we simply put a negative sign in front of the product we just got to get that finally the derivative of the cosecant function is negative cosecant times cotangent. And this is the heart of calculus, to look for approximations that never stop getting better. I know that many of the things I said here need a little more solid base in order to be 100% perfectly correct, but I believe I was able to give you a good intuition for understanding where the approximations used in calculus come from. Thank you for sticking here until the end. That surely means a lot to me. And I hope this video has helped you in any way, and that it stays as a reminder that calculus is made of tiny nudges.